Hi, my name is Ian Fogarty. I'd like to talk to you about Bronstead and Lowery acids and bases. So, in the last section, we talked about acids from an Arrhenius point of view. Now, Arrhenius said that an acid like HCl, right here, would split up into its H plus and Cl minus. And in fact, it was the H plus that was the thing that we associate with an acid being an acid. And this would be a strong acid because it dissociates 100%. And then something like hydrocyanic acid, which would be a weak acid, but again, it splits up into H plus and Cn minus, but not 100%, so it's a weak acid, is what Arrhenius would say. Then we looked at bases, and bases would have the opposite of that. They'd have OH minus in them, so sodium hydroxide, potassium hydroxide, and calcium hydroxide all split up into their ions, and then associated with that is the OH minus. So it's the OH minus that we associate with bases. And that works really well for most of our acids and our bases. Arrhenius did a great job for us. However, we have some problems. For instance, lithium hydroxide, when it splits up into La plus and OH minus, that's normal what we think. But when we take ammonia and we put it into water, it turns out that the ammonia behaves very similar to a base. But where is the OH minus? It's not obvious like it is in LiOH that it would be a base, but yet it does behave like a base. And so there's a problem with Arrhenius's definition. And so Bronstead and Lowery came up with a different idea. There are two different scientists that worked on the same thing at the same times, but they didn't know each other. They came up with the same idea simultaneously. And so Bronstead and Lowery had a slightly different point of view for acids and bases. They said, what would happen if ammonia didn't have OH minus in it, but what would happen if it stole one of the water's H pluses? And so then it would become NH4 plus and OH minus. And so maybe a base doesn't have to have OH minus in it. Maybe it just needs to make OH minus when you put it in water. And so then they changed their definition down here for acids, and they said, well, what would happen if this would react with water, and so water would take away this H plus and give me this weird thing, H3O plus and CH3SO minus. And this has some appeal to it, and the appeal to it is that why, if you're an acid that's got a positive and a negative, and positive and negatives like each other, why would that hydrogen fall off? Why would things split up? And Arrhenius had a hard time explaining that. So Bronstead and Lowery said, well, no, the hydrogen doesn't fall off. What happens is the water rips it off. It gets torn off. And so this is different ideas for what an acid and a base is. And so they would say, for a base, you don't have to have OH minus in it. You just have to make OH minus, where this ammonia steals away an H plus to make NH4 plus and OH minus. And then on the acid side of things, where the water grabs a hold of that H plus to B and gives me acetate and this weird thing. Now this weird thing is called hydronium. So this odd thing is called hydronium. And it looks like this. You have an oxygen with your hydrogen. You have your oxygen with your hydrogen, so there's water. With your lone pair and a positive charge. This is nitrogen with a plus charge, and it's called ammonium. The IUM and the IUM for a positive ion. So you have ammonia and ammonium, and here you have hydronium. So, Bronstead and Lowery came up with different definitions. They said that an acid is a proton donor and a base is a proton acceptor. And many students get confused on why this is a proton donor and proton acceptor. So, well, think about this for a second. If you have nucleus of a hydrogen atom, so there's your proton, And then around the outside, you've got your orbit for the electron. Here's your electron. And that gives you a neutral hydrogen. And so then, if you lose that electron to become H plus one electron, then you would have to get rid of that and you would be left with simply a proton. And so H plus is just a proton. And so they said that an acid is a proton donor and a base is a proton acceptor. So in this case, what we have is the ammonia here and the water. One of those hydrogens is going to be transferred to that nitrogen. The nitrogen is going to come over and swipe it away, and it's going to make NH4, and you're going to be left with OH minus. So in this case, this is going to be the base because it is accepting the H plus, and this is going to be the acid. Down in this situation, the proton that's being transferred is this one right here, and so this is going to go over to the water, and so we have this being the acid and this being the base. Proton acceptor. Notice that water can behave like an acid or a base depending on the situation. So on the last slide, we talked about ammonia being the base and water being the acid. And so the ammonia would steal the hydrogen from the water and make ammonium and OH minus. And so we had this being the base and this being the acid. Now it turns out that this reaction is reversible. So ammonia could bump into the hydroxide again, and the proton leave the ammonium and go back onto the OH to make water and ammonia. And so if that were to happen, this would then be the acid, and this would be the base, because it's receiving the proton. But because it's going backwards, we're going to call it the conjugate acid and the conjugate base. Likewise, down here where we have acetic acid, this H plus could be stolen from the acetic acid by the water and form acetate and H3O plus. And so this would be the proton donor, the acid, and this would be the proton acceptor, the base. However, again, these two things could collide afterwards. And if they did, then the proton could be returned to the acetate. And so this would end up like the base and the acid. But because it's going backwards, it would be the conjugate acid and the conjugate base likewise. Now, the big question is, what about the strength of acids and bases? And so let's suppose that ammonia is a weak base for a really weak base. And so it really has to fight in order to get that proton off of the water to make ammonia and hydroxide. And if that were true, that this base was a very weak base, what about the strength of its conjugate acid? And so if ammonia had to fight really hard to get that proton to come off the water to make ammonium and hydroxide, perhaps when hydroxide and ammonia hit together again to go backwards, it wouldn't be very difficult for the hydroxide to steal the proton back. And so if you have a very weak base, what that means is you'd have a pretty good conjugate acid. However, suppose that ammonia was a stronger base and didn't have to fight really hard to get that proton off at all. The conjugate acid would be very weak because the OH would have to have a hard time getting that proton off. It was easy to get in the first place, and so it's not going to let it go very well. And so the conjugate acid would be very weak if the base is very strong. So if we look down here at the acetic acid and kind of go through the same idea, suppose that acetic acid is a fairly strong acid, then it's going to give that H plus away to the water pretty easily. So what that means is when the hydronium ion collides again with the acetate, it's probably not going to take it back very easily. It gave it up in the first place quickly and easily to be a stronger acid. And so to take it away from the water and after is probably not going to happen. And so it's going to be a fairly weak conjugate base. However, if acetate was a very weak acid, then the water would really have to fight in order to take that H plus off in order to become hydronium and acetate. And so when the acetate bumps up against the hydronium again, there's a reasonable chance that this could actually pull it back and get it back. And so in that case, it would be a fairly strong conjugate base. And so the moral of the story in both examples is that if you are strong on one side, you're going to be weak on the other. So a strong base on one side is going to be a weak conjugate acid. And a weak base is going to be a strong conjugate acid. A stronger acid is going to be a weak conjugate base, and a weak acid is going to be a stronger conjugate base. Okay, I'd like to review water real quick because I want to talk about dissociation of water in a second. And so here we have our hydrogen, oxygen, hydrogen, and so the electronegativity of oxygen is 3.5, electronegativity of hydrogen is 2.1, and electronegativity of hydrogen is 2.1. So what that means is the electrons that are in this bond right here spend more time around the oxygen than they do around the hydrogen. And so this hydrogen is a little bit electron deficient, and this oxygen is a little bit electron rich. So what that means is this hydrogen right here has a partial positive charge. This oxygen has a partial negative charge. Not a full plus, not a full negative, like a 0.1 of a charge or something like that. And so this is the same thing as happening down here with this hydrogen. Okay, so what does that mean? So this has implications for the autodissociation of water. Let's review what autodissociation of water looked like before. When we looked at Arrhenius, you said that water would just fall apart and make H plus and OH minus. And so here is our water, and we would split this bond right here, and it would give you an H plus and OH minus. This would fall apart. And this happens in water all by itself. That's what Arrhenius would say. Now that we have our Bronstead-Lowery idea, maybe we end up with something different. Maybe we have a water here and another water here, and we end up with a hydronium and OH minus. So it turns out that this hydrogen and this hydrogen, let's pick on this guy right here, this hydrogen has a partial positive. An oxygen from an opposite molecule has a partial negative, and so there can be an attraction from this hydrogen to that oxygen. And that attraction can be so strong that it actually, this attraction that happens right here can be so strong, it actually tears that hydrogen off. And if it does, you end up with this H3O plus, which we showed before, and an OH minus. So Arrhenius would say, yeah, water just splits up all by itself. And Bronstead-Lowery would say, well, no, not really. We have this H plus being yanked off by something else, and we form hydronium and OH minus. So in both cases, you have OH minus. Arrhenius, you have H plus. Bronstead-Lowery said H plus doesn't really exist. It really is an H plus attached to water, this hydronium thing. So we often use H3O plus and H plus interchangeably. That often happens. So if we're looking at KWs from Bronstead-Lowery, well, this is what we would have for the Arrhenius, is you have water forming H plus and OH minus, so products over reactants. But we'd say the concentration of water is a constant, and so it would just go away. We would ignore it. It gets included in the Ka. And that would be great. From a Bronstead-Lowery point of view, what does it look like? Well, we just have water, and water is going to be H3O plus and OH minus, and so we have that, and this gets, again, removed because it's a pure substance. And so this would be the Kw, not the Ka. This would be the Kw and the Kw. So again, you see that the H plus just gets changed for H3O plus. Otherwise, it's identical. What about the Kas for the Bronstead-Lowery? So you have an acid here that's the H plus is falling off and leave you with the negative anion. And so then the Ka is products minus reactants all over, products over reactants. And then down here, you have the same idea, but the H plus just isn't falling off. No, water is tearing it off. And so water comes by, takes that hydrogen over to the water, gives you hydronium and the negative ion. The Ka is still products over reactants. That's great. All that happens here. and the water again gets removed, and so that goes away, and we're left with something very similar. The only difference is you have H plus here and OH minus there. So the Bronstead-Lowery idea is simply that things don't fall apart, they get torn apart, and other than the H plus and the H3O plus, things are pretty much interchangeable. Thank you very much for your time.